Okay, December 7, 2021, material for the fourth exam. Okay, chapter 10, from torque on, from torque, including including torque, right? Chapter 11, chapters 11, 12, and 13. Okay, those two chapters are short, 11 and 12. They're not, but chapter 10 is only a partial part of the chapter 10. Only, here you go. 10, 11, 12, 13. Okay, that's what exam 4 is all about. And starting from torque. Okay, start from torque. I cover all of that. I didn't keep records, right? Because I was just displaying that to you. Okay, and so that's what you have to worry about chapter 10. 11, 12, 13, and 11, 12, and 13 also you have to worry. And what we are going to do now, we are going to cover fluids. Okay, fluid statics. Right in here. Okay, we're not gonna elaborate too much. It's gonna be very simple stuff, not much calculus, okay? And I'm gonna do some simple problems. So what you have to know about fluids? Before we start talking about fluids, first we have to define an important parameter in fluid. So here you go. Fluid mechanics. First thing you have to know is the idea, the concept of pressure. Okay. And I'm going to come up with a very simple way of defining pressure. And then we can extend that idea of pressure for other things. Let's see if I have a good... Okay, I'm going to use this one here. Okay, we have this object here that has a weight. Okay? Have this object here, has a weight and has this area here. Has this cross-sectional area and so on. Okay? So the pressure depends on the force and depends on the area that's contacting the surface. That's what the pressure depends on. So if I place this object right here at the top of the table, it is going to exert not just a force, but it's also going to exert a pressure on the surface of this table. Okay, and the definition of pressure is going to be the following. It's going to be pressure is going to be the force divided by the area. Okay? That's the definition of pressure. So you go ahead, take the mass of this object, multiply by G, measure this area that's under contact. It has to be the area under contact, right? If there is if not everything here is contacting the surface, then you have to account for whatever is contacting the surface, right? If there is a hole here, not a hole, but a depression, this depression is not contacting the surface, right? So if you have that depression in there, then the pressure is going to be more because you are going to have a less contact area is going to be less. Okay. But if it's completely flat, you know, then you can just measure this area here and you get the pressure. Simple enough. So now here you go. I go ahead, measure the pressure here, or calculate the pressure. Then you calculate the pressure for this case here. Okay, where in which case the pressure is gonna be more? The pressure is gonna be more here in this case or in this case? Think about that. In which case the pressure is gonna be more? Huh? Here you go. What's happening to the area? How this area compared to this area?
It's thinner. One side is thicker, one side is thinner.
I'm asking the area, right? Thinner means dimension, right? Area is going to be what? Less. Okay? This area is greater than this area, right? This area here is less than this area. This area here is larger than this area, right? So if area decreases and the force remains the same, comma, pressure increases, right? Pressure increases. Now I decide to put, now I decide, I'm not changing the area, right? But now I decide to do something. I decide to apply an additional force on the top. So in addition to the weight of the object, I'm also applying, let's say, 2 newtons to this guy. What's going to happen to the pressure? What's going to happen to the pressure? Huh? The force at the top is increasing, right, in the equation. So what's going to happen to the pressure if the force increases? Here you go. If force increases and the contact area remains the same, what happens to the pressure? That's the question. If the, I'm going to put it this way, if the contact area decreases, right? What pressure? What happens? Also increases, right? Also increases. Pressure also increases. So that's the idea that you have to keep in mind. We can rewrite that in differential form. Okay? You can rewrite that as df dA. Okay, what's the unit of pressure? Simple enough. Do dimensional analysis. Here you go. Unit of pressure is going to be unit of force divided by unit of area. And what do you get? We get Newton divided by meter square. Okay? This unit shows up so frequently that we give a name. We call it Pascal. Pascal, we abbreviate by PA. Okay? There are other units of pressure. There are other units of pressure. And the other unit would be another unit would be the atmosphere. Okay? One atmosphere is approximately 10 to the fifth Pascal. 10 to the fifth. Yeah, 10 to the fifth. 1, 2, 3. Yep. Yep, that's right. It's not difficult to memorize that. It's 100,000 Pascal. It's not exactly, but it's a good ballpark to keep in mind. 100,000 Pascal. So right now here in this room, the atmospheric pressure, the pressure that the atmosphere is exerting on us is 100,000 Pascal approximately, a little bit more. But that's a good enough value. Okay, so that's the definition of pressure for the case of a solid object. This idea of pressure can be extended to gases and liquids as well. Gases and liquids as well. Let me get a drawing here for you. An illustration for you how it works. Here you go. Let me see here. Yeah, I have to create this illustration from scratch. Okay, so just think about the surface of the Earth. I'm gonna use this guy here. Okay, here we go. Here's the Earth. Okay, the Earth is surrounded by by an atmosphere, right? We're gonna get the here you go. The atmosphere is very thin, by the way, compared to the surface, compared to the radius of the Earth, like that. I'm gonna exaggerate the thickness of the atmosphere, like that. Okay, and oops, what happened here? Sometimes it does some funny things. Here you go. I'm going to put little dashes there. Here you go. Here you go. That's the atmosphere surrounding the Earth. Okay, how can we picture the pressure due to the atmosphere? The pressure due to the atmosphere is just the weight of the air column above us. Can you picture that? Okay. So if we go ahead and take, you know, a column of air that extends all the way up to space, this column of air, is gonna have a weight. When you get the weight of this column of air and divide by the area that is in contact with, you can come up and say, look, that's the atmospheric pressure here. Here's the column of air with a given area. It doesn't matter what area it is. Okay. Get the weight of this column of air divided by the area, and you get the weight, the atmospheric pressure. Okay. That's how you can picture the atmosphere, the pressure due to a liquid or a fluid in general. And a fluid means either a liquid or a gas. Okay, so let's write that down. This idea of pressure, force divided by contact area, can be applied not just to solid objects, but also to fluids. And how do I define fluids? It's gonna be either a liquid or gas. Okay, liquid or gas. So any liquid or gas above you exerts a pressure on you. Okay. In the case of the atmospheric pressure, the weight of a column of air divided by the contact area, the weight of a column of air divided by its contact area, is the atmospheric pressure. And we say that nearby sea level, at sea level, the atmospheric pressure is said to be 1 atm, 1 atmosphere, which is approximately, remember, is approximately, the exact number is slightly different, 100,000 Pascal. Can you remember that? That's easy to remember, right? It's not difficult to remember. It's slightly different, but 100,000 gives you less than 1% difference. Okay, so we can, having this idea in mind, it is possible to find out what's the pressure, how the pressure varies with the depth within the depth of a liquid. You submerge yourself into a liquid, it is possible to calculate what's going to be the pressure that this liquid, not the liquid, the fluid in general, is going to be. We're going to do that for the water, and then you can do that for almost anything. Water, mercury, liquid mercury, alcohol, so on. Okay, let's do that. Here you go. The calculation goes like that. You start with a, find, here you go. Find the pressure of water as a function of the depth. Okay, so here you go. So think about that. The deeper you dive, the more water you have above you. The more water you have above you, the higher the pressure, right? The higher the weight of that column of water above you. So the pressure should increase. Now let's see how pressure increases with the depth. That's the whole idea. You know what you should know. You must know the depth, of course, right? As a function of depth, let's put that depth. I'm gonna use the same parameters that I use in my notes. I'm going to use, let's see, h. Yeah, here you go, h. Given the depth, treat that as an exercise, right? As an example. Given the depth of water h and its density, find give the pressure find its pressure as a function of depth. That's how I'm gonna do it. Solution. Insert symbol equation. Here you go. We start with the equation. Oh, I'm running out of battery here. Here you go. Pressure is what's going on here? Okay. Pressure is force divided by area. And this force is going to be what? This force is going to be the mass of the column of water, delta M times G. Okay? Divided by what? Divided by the area in contact with you. So where we can design, we can say that what you have a column of water, and this column of water has an area that's given by pi. You know what? No, I'm gonna leave a. You don't need to. You don't need to do pi r squared. There's a reason for that. Leave like that a. Okay. Yeah. Don't put pi r squared. I'm gonna even put delta a. Okay. Because I'm putting delta m there. Let's put delta a here. And also that should be delta f. Because of df dA. Yeah, let's use that. Df dA. So there is a little mathematical trick that simplifies our equations, okay? And the mathematical trick is related to the mass. The mass can be here written as being the density of the water. The density of the water times what? Times the water volume. The delta V volume. Remember, it's a big cylinder above us. This cylinder has a volume. Oh, it should be delta V, not a delta A. This cylinder has an area, right? A surface area here, and a height h. Okay? Can you picture that? It's a cylinder of water above you. Has an height h and an area delta A. Do you see what happens to the delta A now? This delta A here downstairs is the same as this delta A upstairs. And that's the nice thing about this derivation. Whatever we do not know ends up being ends up canceling out. You usually get things like that in physics. And that's what we get for the pressure due to a fluid, rho hg. Rho g is called the weight density, not the weight, but the weight density. Okay? But that's the pressure due only to the fluid. The above is the pressure due only to the fluid. If you, the actual pressure is going to be the pressure of the fluid, plus the atmospheric pressure. Okay? So here I'm gonna put that. Here you go. That will be the pressure due to the fluid only. Okay, like that. The net pressure is going to be, it's just they're just summing. They just sum each other. Is going to be the atmospheric pressure that I'm gonna call P naught. Plus the fluid pressure rho gh. Now let's play a little bit with these numbers. There is a very nice thing about this number right in here. Okay, I'm gonna do that in Excel. I'm gonna just here you already know this is 1 atmospheric pressure, which is approximately has been measured. Okay, 100,000 Pascal. Okay, what about this one? How does it? What you see right in here is gonna be very easy to picture as well, to memorize as well. Note see that G is what? What's the value of G? Huh? I can't hear you. Yeah, 9.8, but approximately what? 10, right? Approximately 10. We're doing rule of thumb here. It's very good to know how to do rule of thumb calculation. And what about the density of the water? What's the density of water? What's the density of the water? That's easy, right? You must have seen that in chemistry. What is the density of water? Come on, folks. Nobody knows that? I'm gonna write that down here for you. Here you go. Density of water. I'm gonna hit right now. You know what? I'm gonna do like that. I'm gonna continue this equation. You already told me that the acceleration of gravity is 10 meters per second square. Okay, it's a very good rule of thumb to apply here. It's a very good approximation. We are making only a 2% error when we account for 10 meters per second. But what about the density of water? The density of the water is 1 gram per cubic centimeter, right? Remember that?
It's 1,000
Or, or
or
1,000?
1,000.
Wow, what's the unit?
It's kilograms, MO3.
Yeah, here you go. It's, is 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. Okay? And now look what we're getting here. We're getting kind of a round number, right? Sort of a round number. Here, the first number is 10 to the fifth Pascal. The second number is going to be what? 10 to the fourth kilogram cubic meter second square. Okay, if you do the math, I'm not gonna, meter cancel out to meter cube downstairs, it becomes meter square per second. Okay, if you do the math, this unit that you see right in here is going to be, let's see here, kilogram. Uh, let me move this guy like that. Okay, good, better. This one gonna become kilogram meter square. Okay, and second square goes downstairs. Okay, that's what we get. And H is going to be in meter. Okay, and so when you take the units of those three, of those two that here, of those that I'm underlying, that I'm emphasizing, you get Pascal. Okay, so now what can we do? Okay, what's going to happen is the following. For every 10 meters of depth that you dive below the water surface, you are going to increase your pressure by 1 atmosphere. Can you remember that?
Yeah.
Okay, 10 to the 4 times H. For every 10 meters that you go underwater, you increase your pressure by 1 atmosphere. Okay? So from the above equation, we can see that for every 10 meters that we dive below the water surface, the pressure increases by 1 atmosphere or 100,000 Pascal. Oops. Or 100,000 Pascal. So, at the surface of the water is 1 atmosphere. 10 meters below the surface of the water is 2 atmospheres. 20 meters below the surface of the water is 3 atmospheres, and so on. Okay? For every 10 meters, the pressure increased by 1 atmosphere. Very good rule of thumb. Plus and minus 2%. Okay? Plus and minus. The atmosphere pressure, 1 atmosphere pressure is not exactly 100,000. Okay, let's take a look at the exact number. Let's see if I have it here. In my notes. I believe it's 101,000. Let's take. I never remember. Oh, yeah. 101,300. That's what 1 atmosphere is. So by approximating it to 100,000, we make a mistake of 1.3% only. Okay, only 1.3%. That's why I, approximate here. Okay, so you can apply this calculation for different substances, for different fluids, if you know their density. The air has a density of 1.29 kilograms per cubic meter, so it's almost 1,000 times less than water. Seawater is a little bit denser than regular water. It's only 3% more denser. Mercury is 13 times denser than water. Mercury is 13 times denser than water. Let's see, sneaking tool. So now you can start playing games with this thing, and we're gonna see. I'm gonna show to you a very interesting result that we get for mercury when it comes to buoyancy. Let me get this thing here. Here you go. Yeah. Okay, so that's the equation that you have to worry about. Here you go. I wrote down everything for you here in my notes. And then we can start talking about something else that's called buoyant force. We do not have lab today, okay? And by the way, I forgot to tell you. I should have told you at the beginning, no lab today, and we have an exam on Thursday. And by the way, I corrected lab report 7 and 8. Okay, let me put that at the top. Okay, no lab today. And I corrected the reports for labs 7 and 8. It's all there in your group folder. Okay. Let's take attendance and then take a break, and before we get into the buoyance, the idea of buoyance. Excel. Second, yep, today is the 5th, we're in good shape here. Today is the 7th. Daniel Abraham. Nope. Mario Acevedo. Mario Acevedo? Nope. Harun? Harun here? No. Musa? Nobody's coming today, huh? Genesis Bell? No. Jennifer Camarillo? There. Okay. Vincent D'Aloisio? No. Robert Faust? Okay. Pedro Flores? Good. Lawrence Flores? Alexander Garcia? Sung? There. Brian Herrera? Brian Inês? Athena? Jesus Lepp? Cassandra Martinez? Dylan Martinez? Henry Martinez? Leonard Melgar? No. Rafael Mercado? No. Raymond Miramontes? No. Jaime Mondragon? No. Alexis Nigret? Marco Antônio Partida? Armando Pérez? Abraham Pérez? No. Nicolas Pisano? No. Ramon Quintana? Albert Ramirez? Ali? Davidson Paxley? Antônio Vega? Kenneth Villagomez? Patrick Villavazov? Nolan Williams? No. And we have 17. Hang in there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, good. Let's go for our break. It's 6:40 right now. Break till 6. No, 5, not 6. 5:55 p.m. Yeah, see? Huh. Interesting. Back from the break. Okay, just quickly. Again, for the record, right? Final exam on December 16th from 5:30 p.m. to 7:30 p.m. Exam will be on Canvas. Make sure you're logging in at the right day and time. You can do this exam from anywhere you want, open notes, open book, but you cannot have any outside help other than your notes and book. Material for the final, all chapters. 30 to 50% of the questions will be from the chapters we did not cover. From the chapters we did not cover on the other exams. The chapters we did not cover in the other exams. What? Fluid mechanics and temperature. The remaining 50 to 70% of the questions will be from the other chapters. And other chapters mean what? 1 through 13. Okay, that's for the final. I'm gonna put it boldface.
Professor, how many questions are going to be in the final?
15, just like the others. 15, 16, you know. Let's see how it goes. No more than 20. Material for the fourth exam. Okay, from now we can go ahead and buoyancy. Let's talk about buoyancy now. Buoyancy. Buoyant force in the Archimedes principle. Here you go. Let's not buoyancy, but let's put the buoyant force. Buoyant force which gives rise to buoyancy. Buoyancy force and Archimedes principle. There is something interesting about fluids, and we're all familiar with that. You get a container, right? Put water in your container, and remember, right, we have a pressure, atmospheric pressure exerting here on the surface of the water, and we also have a liquid pressure at a given depth h, given by that formula that you saw. Okay? And what else? What else we're supposed to know? Here you go. Okay, there is something else. Everybody knows that when we go underwater, we feel lighter, right?
Mm-hmm.
So we do feel lighter because there is indeed a force being applied to us upwards. Okay? And this force, we call it the buoyant force. It happens whenever you're submerged in any fluid, whether it's water, liquid mercury, alcohol, even here in the atmosphere, there is a buoyant force being applied to us. Okay, we are submerged in the sea of oxygen and nitrogen, and these nitrogen and oxygen are applying a buoyant force on us. But it's not that obvious. It's not that obvious. Don't feel it. But what is obvious is in balloons. Have you seen balloons? How balloons rise? Balloons rise because there is a buoyant force due to the surrounding air being applied to the balloon. Okay? And there's a reason why balloons they rise. And we're gonna see that. Okay? So where this buoyant force arises from? Okay? Okay? Here you go. Here's a very good explanation of a buoyant force. Because the pressure increases as you go deeper and deeper, we end up having a pressure differential from the bottom and the top. At the bottom of this object, the submerged object, the pressure is higher than at the top of this object. And pressure is this funny type of force that exerts a force in a direction perpendicular or normal to a surface, okay? So the pressure, even though you have all this liquid water here at the top, the pressure is not going to be necessarily downwards. The pressure is going to be downwards, can be sideways, and can be upwards as well. And now that you have this differential in pressure, the net pressure is going to be upwards. And this net upwards pressure translates into a force that we call the buoyant force. That's where the buoyant force comes from. Okay? Make sense?
Yes.
Okay, that's why we feel lighter underwater. We feel lighter underwater because of this pressure differential that we feel that we have underwater. Okay, let's see if we have another one. Okay. So what else you have to know? Now we got the conceptual idea of pressure. There's something else you have to know. You have to know too, if you have an object, if you submerge in an object, everybody has noticed that, right? If you fill up your tub there at home at the very top of the tub and then you submerge yourself, the water is gonna
It's gonna rise.
not gonna it's not just, remember, you fill the water all the way down to the top of the tub, right?
Right.
So if you submerge yourself, what's gonna happen to that water? It's gonna overflow, right? Overflow, right? No, of course. If you don't fill until the top of the tub, but just below it, when you submerge yourself, yeah, the water is gonna rise, right? Just like we have here. Now, what else you have to know? You have to know that if you have these objects of volume V, this object has no holes. Okay, it's not. It doesn't absorb water. It doesn't. No holes whatsoever. So what's going to happen? It's going to displace the same volume of water. Makes sense? The water and the object cannot occupy the same place at the same time. So the water must be displaced by the object. That's why the water level rises in the tub, in the bathtub. So remember that. object with a volume V displaces the same volume of water when it is completely submerged. Okay, that's kind of obvious, right? There's no principle here involved, it's just logic. If the object is partially submerged, then the amount of water displaced is going to be equal to that volume of the object that's submerged. Okay? A volume, half of the volume submerged, half of the volume of the water displaced. Okay, and now we are ready to talk about what's the value of the buoyant force. Okay, so here you go. Let's write that down here, right? Buoyant force. Buoyant force. Buoyant. Buoyant force is a force that arises due to the pressure differential between the bottom and top portion of an object. This buoyant force is directed upwards. That's why we feel lighter underwater. Okay, so if you're underwater, the pressure at your foot there is going to be higher than the pressure at your head. And you're going to feel lighter underwater. Your part of your weight is going to be canceled by the buoyant force. Okay, that you have to know. Something else you have to know: a fully submerged object of volume V displaces the same volume of water. Okay? That's what you have to know. And now we are ready to talk about, here we go, Archimedes' principle. It's very easy to memorize. Okay, it's not a law of physics. It was a law of physics at that time when it was discovered in 200 BC. Okay, everybody's familiar with that story, right? Archimedes had to solve a problem to the king. The king wanted to know whether the crown he had was 100% gold or not. And Archimedes starts thinking about that, how to solve this problem. And then one day, inspiration struck him whenever he was submerging himself in the bathtub. He saw the water rising, and the story goes that he was so excited that he started running naked in the streets of Athens, right? Screaming at Eureka, Eureka, I found, I found. That's the story that they say. So what is the principle, which was a principle at the time, right? That he discovered? Okay, has to do with the magnitude of the buoyant force. Okay, I think this principle. This principle today can be derived mathematically. Archimedes principle. The magnitude of the buoyant force of an object is equal to the weight of the fluid displaced. Okay, can you remember that? Memorize that? So you go ahead, you go. You have this volume of water being displaced. You go ahead, collect this volume of water, measure the mass of this volume of water, multiply by G, and that's going to be the buoyant force. Okay? That was going to be the buoyant force, the weight of the displaced fluid. Doesn't matter if it's water, doesn't matter if it's air, doesn't matter if it's CO2, doesn't matter if it's liquid mercury. Okay, so that's how you quantify the buoyant force. Okay, and now let's take a look at the possible, let's take a look at the consequences of this principle. Okay, so here we go. Let's see here. Yeah, here I'm just deriving the Archimedes principle in terms of the differential in pressure, okay? That's all I'm doing here. I'm not going to do that now. So if you want to look at that. So here you go. Here the Archimedes principle in terms of equations. Archimedes got that. At that time, since they didn't have the algebra, Archimedes couldn't derive what I derived here, okay? Algebra was invented later on. Today we know that the buoyant force is due to the differential in pressure times the area. And then we do this math. Now you get delta mg, which is the mass of the displaced fluid. So here you go. The mass of the displaced fluid is the volume of the displaced fluid times the density of the displaced fluid times g. The weight of the object is going to be mg. And now we can start playing some games with it. Okay, so let's go ahead and write in here. Let an object of mass m and volume bv be totally submerged inside in a fluid of density rho. Okay? Of non-density rho. Find the buoyant force applied to the mass. Example. Solution. Okay. So the situation is like that. Buoyant force is the mass of the displaced fluid times the acceleration of gravity. It's the weight of the displaced fluid. And the weight of the displaced fluid can be written as the density of the fluid. So let's put that here, fluid, right? Times the volume times G. Okay? That's what it is. That's the buoyant force. So we can numerical example. Numerical example. 1 V equal to 1 cubic meter, and the fluid is water. Right? What we get? You're gonna get fluid is water is 1,000 kilograms per cubic meter. Here you go. Let's see, 1 cubic meter, yeah. 1 cubic meter. And the acceleration of gravity is what? 10 meters per second square. Like that. And then what we end up getting? Kilogram meter, see? Meter cubic cancel out with meter cubic. We get 10,000 newtons. Okay? 10,000 newtons. Now the question is another example. An object sinks underwater using Archimedes' principle. How does the density of the object compare to the density of the water? Okay, another example. Okay, so here you go. Let me show you a drawing of that solution. Think about that, right? What time is that? 6:20. Okay, we have time. So here you go. We have this situation here. The object sinks. If the object sinks, what does it mean? It means that the weight must be greater than the buoyant force, right? Makes sense? That's what we have here. So the condition for the object to sink is that mg must be greater than the buoyant force. And now let's develop what's going to be the consequence for the density, okay? Since the object sinks, it means that its weight is greater than the buoyant force. Okay, so here you go. I'm gonna write that down. So the object is fully submerged. An object fully submerged. I'm gonna put it like that. Fully submerged sinks underwater. Okay, so here you go. Mg, if the object sinks, must be that mg is greater than the buoyant force. And let's not forget that mg must be greater than the density of the fluid, the volume of the displaced fluid, and acceleration of gravity. But let's not forget that m can also be rewritten as being the density of the object times its volume. How does the volume of the object compare to the volume of the displaced fluid? If the object is fully submerged, you go, the volume of the object here is going to be the same as the volume of the displaced fluid, right? So what's the next step? We can cancel d and g, and what we're left with, if the object sinks, it is because its density is greater than the density of the fluid. Okay? Then we can go for the other case. There are three cases. Object sinks, object floats, and object remains neutrally buoyant. Okay? Sink, float, neutrally buoyant. Go. So now we're going to do that. An object fully submerged. An object initially fully submerged. Just like your styrofoam block that we force underwater, right? Think about that. Have you tried to do that? Get a styrofoam block and force it underwater. You release the styrofoam block, what's going to happen? It's going to shoot upwards. Okay? The buoyant force is so strong in this case, right? That the object just move very quickly upward. An object is initially fully submerged. Is initially fully submerged. Using a chemical principle, determine how the density of this object of the object compared to the density of the water. So it's the same situation. The same situation. It's the opposite situation, right? Here you go. Here you go. It's like that. The object is floating. It means that when it was fully submerged, the buoyant force was greater than the weight of the object. Okay, so we are gonna change this inequality sign. And so we find the condition for an object to float. Its density must be less than the density of the fluid. Okay? So balloons rise in the atmosphere because the overall density of the balloon, the average density of the balloon, is less than the density of the surrounding air. Okay? Makes sense? But it's a buoyant force that propels the balloon upwards. And then we have this other situation. You have to know what neutrally buoyant is, right? It's neutrally buoyant. Neutrally buoyant, what does it mean? Buoyant. It does not sink nor float. Just stay, in the same depth. Fishes are very good at doing that. Using Archimedes' principle, determine how the density of the object compared to the density of the water. So here you go. Let me see if I have it. Okay. Let's see here. Oh, neutrally buoyant. Buoyant. What is it? I don't like that. Yeah, net force is equal to 0. If the net force is equal to 0, it means that the buoyant force is equal to mg, right? So that's how you illustrate that. Mg equal to buoyant force. Rho Vg equal to rho of the fluid Vg. If you want to become neutrally buoyant, you have to make sure that your overall density, your average density, is going to be equal to the density of the fluid. Okay? And that's a very important skill to have if you're practicing scuba diving. Okay? People teaches you how to become neutrally buoyant because it's very convenient when you're diving underwater to be neutrally buoyant. But even, and there's something interesting about the human body, okay? The human body can change its density because we have all sorts of cavities in the human body. The lung is one of the cavities in the human body, right? And we can change the density of the human body by breathing in air and expelling air. Make sense? When I breathe in air, fully inflate my lungs, my density becomes lower because I have lots of air there inside. When I expel the air, my density increases, my overall density increases because I don't have air in my lungs anymore. So you can use this knowledge to become neutrally buoyant underwater or even at the top of the water. Okay, you can, if you swim, you can have access to the swimming pool, you can practice that. You go to with a snorkel, right? Make sure everything is safe and float, with your lungs completely filled. As you start to empty your lungs, what's going to happen? You're going to start sinking underwater. So the density of the human body is very close to the density of the water. Okay? If you have your lungs completely full of air, you're going to float underwater. If your lungs are completely empty of air, you're going to sink. Okay? Make sense? You can do this this experiment when you go, and fishes too. They know how to do that. They can stay neutrally buoyant easily. And when you go scuba diving too, you are carrying a compressed air tank in your back, and you also carry some weights. Have you ever seen that? I end up learning that when I start doing scuba diving. They give you a belt where you put weights in your belt, so you can counter the effect of the air tank, of the compressed air tank, and also the not only the compressed air tank, but also the effect of your, how do we call it? It's a vest. I forgot the name of that vest. It's a vest that you pump air into it, so you can change your overall density. Okay, the compressed air tank pump air into a vest that you're wearing. Okay, so the more air you have in the vest, the less dense of the lower the overall density you're gonna have. And that's applications of this knowledge. Let me see if I have anything else. Yeah, that's all we have for this chapter. Okay, next time we're gonna do temperature, and it's gonna be our last meeting. Any questions that we have here?
But Professor, instead of the lecture for the final, we said from 5:30 to 7:30, that that's the time frame that you have to start able
Yeah,
to get to that final time, right?
yeah. You're not gonna have a 24-hour window.
Oh, okay.
You're not going to. Let's specify here, right?
Yeah, no, I understand.
You're not going to have a 24-hour window. Gosh, you gotta tell everyone so they don't get confused. Okay, no lab today. Final exam, 5:30 to 7:30 p.m. in Canvas. You will not have a 24-hour window to do this exam. Okay, let's okay, go. Why is it not doing that? It was clear, right?
Yeah.
I guess I mentioned that before, right?
Yeah.
So make sure you tell the other students that they didn't come, so they don't miss the final exam. It's very important.
There's a 5 on the 24.
There's what?
No, there's a 5 on the 24.
524. Oh yeah. You will not. Thank you. To do this, you will not have a 24-hour window for this exam. To do this exam.
The final, right?
Yeah.
Okay, then.
Final exam. Yeah.
Oh,
Like the others. The other ones you had a 24-hour window, but not the final.
oh.
Okay. Oh. You go. Okay. Any more questions? Okay. So I see you Thursday. Let me check here one thing. Open file location. Ah, you can download, huh? Google Drive. Google Drive. No. Oh boy, that's my. You know what?
Oh, Professor, and then for my final is my table will actually be adjusted, right?
Yeah, yeah.
Okay. I'll make sure.
No need to- yeah.
Thank you. Okay, so uh, look, I do not know what to do. Okay, so I got it here. And